Okay, welcome back, Year 12. We're looking at absolute maximum and minimum values today. So as you can see here, in the past we've looked at local maximum and minimum values, but today when we're talking about absolute maximum and minimum values, it's really about when the function is defined for an interval. So in this particular case, it says here the actual maximum value of the function is called the absolute maximum, and the actual minimum value of the function is called the absolute minimum. And it says, note, these corresponding points on the graph of the functions are not necessarily stationary points. So let's have a look at some examples to hopefully clear this up. So example 20 here has an interval between -2 and 4. It's asking us to find the absolute maximum value and also the absolute minimum value for the function. So again, let's consider plugging these things in and consider sketching it between -2 and 4, the interval. When you have sketched it, you can clearly see in this particular case that the maximum value occurs at the end point here of the interval. So when x equals 4, substituting it in, we find out that the maximum value is 18. Yep, you can see it's the maximum there. Some people might be tempted to just go, okay, well, let's substitute in the other end point of the interval, -2 in, and find out what's going on. Okay, well, in that particular case, it's 6. Clearly, as we can see here, that isn't the minimum value. So in this particular case, the minimum value occurs when x equals 0 and its value is 2. So as it says here, note that the absolute minimum occurs at a stationary point of the graph. So in this case, stationary point is the minimum. However, the absolute maximum occurs at an endpoint. And it's just making a note here that it's not necessarily at a stationary point. It could be at somewhere else in between in that interval. So again, example 21, it lies between the interval -2 and 1 for this function here. Again, it's saying, hey, find the maximum and minimum values. So again, like if you just said, okay, let's consider the stationary point. Well, in this particular case, the stationary point here is at 0 and the value is 2. It's neither the minimum or maximum value. Yep, so you can't just go, okay, it's going to occur where the stationary point is. So in this case, again, consider the shape of it. We're looking at the endpoints. When we plug in x equals 1, the value is 3. And when we substitute in -2, the endpoint is -6. And just by virtue of looking at this graph here, you can see that at those endpoints of the interval, it is going to be the absolute minimum and absolute maximum values. Yep. So you can be asked to apply this in different scenarios. So we've got the classic square piece of paper, or oh no, it's metal in this case. And it's got a side length of 2 meters. It's a square. They're saying, hey, if you cut out 4 little squares on the side, you could fold it up and make a little a box. And so then it would have a height of x. Yep. So each one of these bits here is an x. I don't know whether I can draw it on easily here. An x, and then there's an x there, x, so forth. Yep. It's saying, hey, show that the volume of the box v meters cubed is given by this formula here. So again, what you need to consider is that the side from here, from here to here is 2 meters. If you cut off the ends here, that is x there, you cut off an x there, the length is the same as 2 take away 2x. Because it's a square, this is also going to be 2 take away 2x. Yep. So just see how successful we are. 2 take away 2x. 2 take away 2x. Cool. Now, hopefully you remember how to calculate the volume of a shape. Volume is obviously the length times the width, that's a W, times the height. So we've got the length was 2 take away 2x, the width was 2 take away 2x, so that times that is going to be it squared, multiplied by the height, which is going to be obviously x there. So that's where we get the volume there, 2 take away 2x squared, length times the width, multiplied by the height, which is x. Expanding things out, happy days, we get this here. Surprise, surprise, it expands out to 4x cubed, take away 8x squared plus 4x, which is us showing that there. Next, it says find the value of x that gives the box its maximum value and show that the volume is a maximum for this value. So again, what we can do is apply our knowledge of differentiation. We can differentiate this equation and obviously find out where the stationary point is by making it equal to 0. V dashed x, we are differentiating that. 3 times 4 is 12, x squared. 2 times negative 8 is negative 16. Take away 1 from the power, it's x plus 4. Cool, we have differentiated it and we're also making it equal to x to find out the stationary point. Again, we can divide everything by 4, divide that side by 4, divide this side by 4, we get to here. This can be factorized. 3x take away 1, x take away 1. And from here, using the null factor law, that's not going to write NFL, a null factor law, either this bracket here is going to be equal to 0, which means x will equal 1/3, or this here, x take away 1 will equal 0, which is the same as x being equal to 1. So we've got two solutions here, but here is the catch. In the real world, we need to think about the process here with this. And if you have a box and you've got the length is 2 take away 2x, if you cut 1 in from both sides, 1 that way, and you cut in 1 from this side, your box width is going to be 0, or the length is going to be 0. So you can't actually cut in 1 from both sides and still have that length. So you won't have a box if you do that. So the one that we need, the value you need to consider is just x equals 1/3. So cutting in 1/3, cutting in 1/3, you'll still have something there. Now, so we've found the value that gives us the maximum volume, but just to actually show that it is the maximum volume, what you can do is determine the nature of what's going on. So again, these little graphs or these little tables are useful. We know that at 1/3, the derivative is a stationary point. It's like that. If we check to the left, see what the slope is. So just choosing a value, you might choose, I don't know, 0.2. You'll find that it's a positive gradient on the right. Oh, sorry, on the left. Checking a value to the right of that, it's going to be a negative slope. So when it goes like that, obviously we know that's going to be the maximum point at the top there. Yep, that's why they've showed that. So if we know that the maximum volume occurs when x equals 1/3, to find out what the actual volume is going to be, you can substitute that back into the volume formula. So whether you substitute it back into this here, they've substituted it just back into this part here. It's the same thing. Yep. When you substitute in 1/3 into there, we get 16 over 27 meters cubed for that. Part C was asking you to sketch the graph of V against X for a suitable domain. Again, I guess what they're saying is, as we discovered, you can't have anything more than 1 as the value for X, because it's just going to end up being negatives for that. So sketching it between 0 and 1 is useful, and notice here that they've put on that maximum value, which happened when x equals 1/3, and we know its corresponding y value was 16 over 27. It says here, if the height of the box must be less than 0.3 meters, i.e. x is being less than or equal to 0.3, what will the maximum value of the box be? So in this case, says here the local maximum of v of x defined between 0 and 1 is at this particular point here, 1/3 and 16/27. But if we think about this here, at that there when x equals 1/3, whoop, imagine I've drawn a nice straight line there. That third, that maximum value, isn't in the interval between 0 and 0.3. Imagine I've drawn 0.3 there. 1/3 is just past 0.3. It's like 0.3333. So they're actually looking for the value just before that. Maybe I can draw an arrow. Yep. So in this particular case, because we're just finding out what's happening at 0.3, not 1/3, which is 0.333, what we need to do is substitute in x equals 0.3 in there, and then we enter the volume formula and find out what the maximum is at that particular, or sorry, not the maximum, finding out what its value is at that particular point, and it is 0.588 meters cubed. So it's going to be a little bit different. If the height of the box has to be less than 0.3, the maximum volume of the box is going to be less than if it was at 1/3. Again, thanks for listening. Good luck with this exercise. Bye for now.